Welcome to our lecture on variable selection techniques. Imagine you are packing a backpack for a long mountain hike. If you pack too few things, you are unprepared. If you pack everything you own, your bag is too heavy to carry. Building a statistical model works exactly the same way. Today, we will learn how to find the perfect balance of variables to make our models both accurate and easy to use.
Now that we understand the goal is balance, let us look at what happens when we get it wrong. When we build a regression model, we might be tempted to throw in every possible factor. However, including irrelevant or redundant factors actually harms the model. This increases the variance of our predictions, causing a problem known as overfitting. Overfitting means the model memorizes the random noise in our specific sample data, rather than learning the true underlying relationship. Variable selection is the systematic method of evaluating different combinations to cut out the useless data, allowing the true pattern to shine through. To choose the best variables, we need a mathematical way to score different models against each other. You might immediately think of the standard coefficient of determination, or R-squared. While it measures how well the model fits the data, it has a major flaw. It always increases when you add more variables, even if those variables are completely useless. It gives an unfair advantage to complex models. To fix this, statisticians realized we need a metric that applies a mathematical penalty for every new variable added. If a new variable does not significantly improve accuracy, the score should actually drop. This brings us to the adjusted R-squared metric. Conceptually, this formula takes the standard R-squared and shrinks it based on how many variables you use. Let us break down the symbols. R-squared adjust is our penalized score. R-squared is the standard unadjusted coefficient. The variable n represents the total number of observations in our sample, and p represents the total number of parameters including the intercept. Notice the denominator, n minus p. As you increase the number of parameters p, this denominator decreases, making the entire penalty fraction larger. This ensures we only keep variables that provide a massive boost to predictive power. Before we move on, let us see this formula in action with a concrete example. A researcher is predicting house prices using a dataset of 50 houses. They have two models. Model A uses 3 parameters and has a standard R-squared of 0.80. Model B adds a new variable, bringing it to 4 parameters with a slightly higher standard R-squared of 0.81. We need to determine which model is better. We will start by evaluating Model A to establish a baseline. We substitute our given values into the formula, preparing to penalize the model based on its 3 parameters. Continuing with Model A, we simplify the terms. The term inside the parentheses, 1 minus 0.80, gives us 0.20. This represents the 20% of variance that remains unexplained by Model A. We multiply this unexplained variance by 49, which is the total sample size minus 1. We then divide by 47, the degrees of freedom for the error. This fraction evaluates to approximately 0.2085, which is our penalty term. Subtracting this from 1 gives us a final baseline score of 0.7915. Now that we have our baseline, we move on to evaluating Model B using the exact same mathematical framework. We substitute the slightly higher standard R-squared value of 0.81. We keep the same sample size of 50, but we must increase the parameter count to 4. The unexplained variance drops slightly to 0.19, which is good. However, the denominator decreases to 46 because we added a parameter. This smaller denominator causes the overall penalty fraction to become larger. This is exactly how the formula punishes us for adding complexity. Let us finalize the calculation for Model B. Subtracting the new penalty term from 1 gives us a final adjusted R-squared of 0.7976. We can now directly compare this to Model A.
Since 0.7976 is greater than 0.7915, model B is the mathematically superior choice. Physically, this tells us that the slight increase in raw accuracy from adding the new variable was indeed large enough to overcome the penalty of adding it. The new variable is genuinely useful for predicting house prices.
While adjusted R-squared is great for variance, it is not the only tool we have. Another highly popular metric for scoring models is Mallow's CP. While adjusted R-squared focuses on the percentage of variance explained, Mallow's CP focuses on estimating the average squared error of our predictions. It works by comparing the error of a smaller, proposed model against the error of a massive baseline model that includes every single variable available. A well-fitting model will have a CP value roughly equal to its number of parameters. If it is much larger, the model is heavily biased.
Let us look at the mathematical engine behind Mallow's CP. Conceptually, this formula measures how much worse our small model is compared to the best possible full model, while adding a penalty for size. The term SSEP stands for the sum of squared errors for the smaller model with p parameters. MSE full is the mean squared error of the full model, serving as a baseline. The variable n is the number of observations. Finally, the term 2p acts as a strict penalty. As you increase the number of parameters p, this penalty grows, preventing you from adding useless variables just to lower the error. Let us apply this formula to a new scenario. Suppose we have a full regression model with many parameters, and its mean squared error is 10. We propose a smaller model that uses only 4 parameters. This smaller model has a sum of squared errors of 280. Our sample size is 30. We need to calculate Mallow's CP to determine if this smaller model is a good fit. We start by writing out the standard formula. By setting up this equation, we establish the framework needed to see if our smaller model is suffering from too much bias. Continuing with our evaluation, we carefully substitute all of our given numerical values into the formula. The sum of squared errors for our smaller model, 280, goes into the numerator. The mean squared error of the full model, 10, goes into the denominator. We insert our sample size of 30 and apply the parameter penalty by multiplying 2 by our parameter count of 4. We perform the basic arithmetic, dividing 280 by 10 to get a ratio of 28. We multiply 2 by 4 to get 8. We are now left with a simple addition and subtraction problem. We complete the calculation to find our final answer. 28 minus 30 plus 8 gives us exactly 6. We must now interpret this number by comparing it to our parameter count, which is 4. Since 6 is reasonably close to 4, this smaller model is a decent candidate and fits the data fairly well. However, because 6 is still somewhat larger than 4, it tells us physically that there might be a slight bias. The model is likely missing some important information, and we might want to test a model with 5 parameters to see if we can get a perfect match. Now that we know how to score models, how do we actually find the best combinations? Testing every possible combination is called best subsets regression. But with dozens of variables, this becomes mathematically impossible. Instead, we use stepwise selection methods. Forward selection starts with an empty model and adds the single best variable one at a time. Backward elimination does the exact opposite, starting with all variables and removing the least helpful ones. Stepwise regression is a clever hybrid. It adds variables like forward selection, but constantly double-checks if previously added variables have become useless, removing them if necessary. While stepwise selection was the standard for decades, modern statistics often relies on regularization techniques known as ridge and lasso regression. Instead of making a hard binary choice to either keep or completely drop a variable, these methods apply a mathematical penalty to the size of the coefficients themselves. Ridge regression shrinks the coefficients of less important variables very close to zero, reducing their impact. Lasso regression goes one step further and can shrink coefficients exactly to zero. This effectively performs variable selection automatically, making these modern alternatives highly preferred in practice today. To visualize everything we have discussed, let us look at the bias variance trade-off graph. On the horizontal axis, we have the number of variables, representing model complexity. On the vertical axis, we have prediction error. Notice the blue curve representing training error. As you add more variables, it always goes down, tricking you into thinking the model is improving. But look at the red curve, the testing error on new data. It eventually starts to rise again, forming a U shape. The lowest point on that U shape represents our optimal subset of variables, balancing bias and variance perfectly. We have covered a lot of ground today, so let us review our key takeaways. First, variable selection is the critical bridge between collecting raw data and building a useful predictive model. We must balance underfitting and overfitting. Second, we cannot rely on standard metrics. We must use penalized scores like adjusted R squared and Mallow CP to fairly evaluate models. Finally, modern techniques like lasso regularization allow us to filter out the noise automatically. You now understand how to ensure your final model is simple enough to understand but powerful enough to make accurate real-world predictions.